Okay, good morning everyone. Welcome back. It is cold and some of the students are not here because of flu, I guess. So please take care. Anyway, so last time we talked about how to solve economic dispatch, and the example was the most simplest one. Our cost function is quadratic function and we have only one constraint. The constraint is about satisfying the demand. So the sum of generation equal to the demand. And we have this kind of curve. This kind of curve. X-axis is generation of each generator and y-axis is the price, the marginal cost. So this figure shows the incremental cost or marginal cost of two generators, generator 1 and 2. So because each generator wants to produce economically, the marginal cost curve gives us the generation strategy given the price, given this price. So when the price is lambda here, and then you go to this direction and you find the amount of the generation of each generator. So by changing this price by the operator, each generator can vary their output, and the final goal is to the sum of the generation is same to the demand. Okay, so and one of the way to find the solution that satisfies the constraint is based on lambda iteration, and this is actually just a root finding algorithm, okay, as we discussed before. So in this example, we have 30 buses. Actually, IEEE 30 bus, IEEE 118 bus, so they are typical examples. So there are 30 buses, and we have how many generators? I guess 1, 2, 3, 4, 5. There are 5 generators. Okay, so this is the price, lambda, Lagrange multiplier, and this is the marginal cost or incremental cost of each generator. Okay, then for given price, you see different amount of generation. So this is the simplest example because here we do not consider the maximum or minimum limit of each generator, but later we need to consider that. Each generator has obviously maximum limit, but also it has minimum limit. Okay, when it is turned on, at least it needs to generate like 100 or 200 megawatt, etc. So okay, that's next topic. Generator megawatt limit. Generators have limits on the minimum and maximum amount of power they can produce, and typically the minimum limit is not 0. Okay, and because of varying system economics, usually many generators in a system are operate at their maximum megawatt limits. So that means the efficient generator typically operate at its maximum. That is the way of minimizing the total cost. Okay, and base load generators are their maximum limits. So these base load generators are the cheapest one. Okay, except during the off-peak hour. So lambda iteration with gen limits is that in previous example, we do not have we have a lower limit. Actually, we should have lower limit and upper limit. And okay, you may think, we have upper limit, etc. But when you change lambda, they do not. So they are within this range. So we didn't need to consider. We didn't care about whether we satisfy the upper or lower limit. But when we have the constraint, so he is alive, fortunately, even if he had dinner with someone who had flu, your friend is ill now. So, anyway, so when we have a lower or maximum limit, but still we can apply the same lambda iteration. And the method, okay, this is tedious, so I want to skip. So where is the figure? Oh, we don't have the figure. So anyway, when there is a limit, now you can just modify this curve, like, so if it has a minimum limit like that and maximum limit like that, then yeah, you put this kind of line. So the supply curve is just that. So even if price goes up, the maximum generation cannot change. Okay, so anyway, even in that situation, you can apply lambda iteration. You see what I'm saying? Okay. So this is about that. So I want to skip this part because this is an obvious thing. Inclusion of transmission losses. Okay, first, economic dispatch without considering maximum or minimum generation limit. And then we need to consider transmission losses. So previously we didn't consider that. And so this is our new Lagrangian, okay, the cost, the sum of all the generators. And previously we didn't have this loss term, okay? The sum of generation needs to be equal to the demand. But now some part of the power is lost. So this is that. So total generation need to satisfy total demand plus total losses. But the difficult part here is that this loss is not easy to compute, because to know this loss, you need to compute the power flow using Newton-Raphson. Okay, so when the output of each generator changes, power flow changes, and loss changes. So this loss function is complicated. Anyway, we have this loss function in the constraint, and then so yeah, that is here. So how can we do this? Well, so this is not convex optimization. Okay, previously up to this point we talked about convex optimization, but when we include this loss, this is not necessarily convex optimization. So we only care about a necessary optimality condition now. Okay? Yeah, this is nonlinear function. This is nonlinear function, and this is equality constraint. So when we have a nonlinear function in equality constraint, that is not convex optimization. Okay? So this is non-convex optimization, but still we want to find some point, and so this is the necessary condition. Okay? So again, this is a modified Lagrangian, and our necessary optimality condition is still take the derivative of Lagrangian with respect to PGI, and we have the still same equality constraint. I mean, a modified equality constraint. So when you take the derivative, we have this term. Previously we didn't have this term, but now we have that term. Okay. So let's see. This is the marginal cost of each generator. It was the SMP, Lagrangian multiplier, but that is multiplied by something. So, okay, same equation, and just divided. Move this part to the right-hand side, and then divide that by this term, and then you get this one. Then we define this as Li, just a definition. And the meaning of this Li is that this is the penalty factor for ith generator. So this is not a Lagrangian, okay, just a penalty factor. Okay, and let's look at this. What is it? If you increase the generation of ith unit, and if the loss increases, this is positive, and this is less than 1 anyway, then if you generate, then you increase the losses, then this Li is greater than 1. Right? So in that sense, this is a penalty factor. If your contributes increase the power losses in the system, you should be penalized, and vice versa. Okay. So, well, yeah, marginal cost or incremental cost times this is Li, and they are all same. They are all same to lambda. Okay, so that is this one. L1 IC1 PG1 equals Li ICI PGI dot dot dot, and that is same to lambda. So let's interpret what it means. If a generator, for some generator unit I, and if Li is greater than 1, what does it imply? If this is greater than 1 and this is constant, then this marginal cost decreases. What does that mean? For that generator, for generator I, if Li is greater than 1, then the marginal cost at the generator should be lower than before. That means the output of the generator reduces. Okay? Because if I generate more, I contribute to increasing the power losses in the whole system, and that is not good. So that generator needs to be discouraged. Okay? So the lower marginal cost means less generation. Okay, so that generator decrease its output power, and vice versa. Okay. Oh, another survivor. Welcome. So then, how can we compute this penalty factor Li? And yeah. From definition, that to compute Li, we need to know this derivative, how the generation, increasing the generation at ith unit contributes to increasing the losses in the system. But this is complicated function, right? So we just estimate it numerically. That means by increasing the generation somehow, like delta, and for the given delta, you solve the power flow equation again, and then you just compute the loss variation. Okay, so just this can be numerically estimated. Okay, that kind of method is not that bad, because yesterday I talked with Ho-Jin and in mechanical engineering, there is a very famous method which is called finite element analysis. 유한 요소 해석. Okay? And that is nothing but just we have continuous variable, but discretize it and approximate. Okay? Anyway, so this is 2-bus penalty factor example. Bus 1 slack bus, bus 2. Okay. System losses this much, and then we increase the output of 100 from 100 to 110 and check how much the loss increases, actually decreases. Okay, so delta PG2 is 10 megawatt, and compute power flow and check the power losses difference. That is this one actually. So power losses are decreased. So then you just compute L2 like that. Okay. So this is less than 1. Okay. So this is analytical result, and this is kind of empirical numerical result, and they are very close. 30-bus economic dispatch example. So now consider losses. Because of the penalty factors, the generator incremental costs are no longer identical. So even if we do not have transmission limit, the generator can have different cost, different price, okay, because of the power losses. And you see that these 2 generator get this price, this 3 generator gets this price, etc. Okay, this will be more complicated when we consider transmission line limits. Okay, and that is very important part. And because the problem happens when the transmission line meets its limit. Okay, and if more and more lines have that kind of a limit condition, then that means we are very vulnerable to some kind of contingency. Okay, and then also in that case, so when many loads are heavily loaded, that means solving the power flow equation numerically may not be stable. Because if you want to use Newton-Raphson, you need to compute Jacobian and take the inverse of that. But at that moment, when the system is congested, then the Jacobian, the condition number, can be very huge, like 10 to the 6, 10 to the 7. Okay, so numerically unstable. So that means feasibility is very important later when you solve optimal power flow using deep learning. Okay, area supply curve is that. So far, we focus on supply curve or marginal cost of each generator. So we have several this curve, but you can just sum them up. Okay, so when this is one area, there are 5 generators. Just sum them up, and you have a single supply curve that is called area supply curve. So this is the result. The area supply curve shows the cost to produce the next megawatt of electricity. So this is the marginal cost, okay? Assuming area is economically dispatched. Okay? So you may think this is the result of economic dispatch using lambda iteration or some other method. Okay? So for given price, that amount of generation, that price, that amount of generation, from the result of economic dispatch. You see what I'm saying? No. No. Why not? Why not? So here we know how to solve economic dispatch considering power losses, right? And then, yeah. So after you solve economic dispatch, you can decide at this price, this amount of generation is possible. So just sum all the generation at the price, and then you have one curve. Okay. So economic dispatch summary. Economic dispatch determines the best way to minimize the current generator operating cost. And lambda iteration method, actually this is a bisection method, is a good approach. Bisection is typically robust for solving the economic dispatch problem. And generator limits are easily handled, and penalty factors can be used to consider the power losses. But this economic dispatch does not consider whether turn on or turn off the unit. So if the optimization covers turning on or turning off, then that is called unit commitment problem. So this unit commitment problem needs to be solved first. And actually this is a combinatorial optimization problem because it has binary decision variable, turn on, turn off, 1 or 0. So first solve unit commitment problem, and after we decide which generators are on, then for the turned on generator, we solve economic dispatch. Okay, but so far we didn't consider transmission line limits yet. Okay. Any questions so far? So far very easy. Okay. Let's move on. By the way, so dispatch means 급전, economic means 경제. So economic dispatch is 경제 급전. But dispatch, the meaning of dispatch is like dispatch. It's the name of what? You know what I'm saying? No. Dispatch. YouTube or something like that. Just kidding. Okay, never mind. Okay, next topic is security constraint economic dispatch. So the meaning of security constraint is slightly different when we talk about security constraint OPF. We didn't cover that yet, but here security constraint is slightly different from the SC OPF .SC. Okay, so here security constraint does not consider contingency. Here the security constraint means just we need to consider the transmission limit. Okay, so a security constraint economic dispatch is almost same to optimal power flow. But the only difference is that security constraint economic dispatch only focus on the output of the generators. Okay, so considering the limits and power losses, what is the most economic way to generate? But in optimal power flow, we may have different objective function other than the cost of generation.
결국에는 저 security constraint ED가 ED의 constraint에 추가적으로 generate limit이랑 power loss 같이 들어가는 상태가 저 security constraint ED라고.
Yes. Yes. So yeah. So
지금까지 그러면 저 SCED
지금까지 뭘 했는데요? what did we do so far?
제너레이터 리밋이랑 트랜스미션 로스까지 고려를 했잖아요. 그 전에서 그게 시큐리티 컨스트레인트인가요?
No. So we also need to consider transmission limit.
아, 트랜스미션.
Yeah, transmission limit, generator limit, and power losses. Okay, considering all the three, and economic dispatch. That is security constraint economic dispatch, and that is almost same to optimal power flow, okay, which is our last topic. But optimal power flow is a superset of security constraint economic dispatch in the sense that in OPF, your objective function can be the cost of generators, okay, which is same to economic security constraint economic dispatch. But sometimes you can have just power losses in objective function in OPF. So OPF can formulate several things. Okay. Anyway, so transmission constraints often limit ability to use lower cost generator, and such limits require deviations from what would otherwise be minimum cost dispatch in order to maintain system security. So, the security means the supply and demand meet together. So, the goal of security constraint economic dispatch, or OPF, they are used interchangeably here, is to determine the best way to instantaneously operate a power system considering transmission limits. This is really critical part. I want to emphasize again. Okay, considering transmission limit is very critical. So, and usually this best, another survivor. So I'm happy to see you. So usually best means minimizing operating cost while keeping flows on transmission below its limits. And in 3-bus case, we have 3-bus case next. So in 3-bus case, the generator at bus 3 must be limited to avoid overloading the line from bus 3 to bus 2. Let's see, bus 3, bus 2, security constraint economic dispatch. So load, another load, and this is congested. So need to keep line from bus 3 to bus 3 to bus 2, this line from overloading. Yeah, so now we have this constraint, another additional constraint in economic dispatch. So that is security constraint economic dispatch. So, okay. So we are talking about power flow and optimal power flow, but actually power flows based on physical law. Okay, right? So there is network topology, and there are some impedance, and then we know the complex voltage, and then power flows, right? But sometimes we have you remember balancing authority area 1, 2, 3, and they have some transaction. So because when they have low generation, then they want to import power from another area. Okay, so that is a power transaction between two areas. So in the case of multi-area operation, our desire is that this is area 1, and this is area 2, and maybe there is a power transaction which was made in advance. So they expect to import or export some amount of power. But anyway, this is a power system, and there are another area like this, and anyway they are somehow interconnected, right? So sometimes we have undesired or unexpected power flows. Okay? So that is, yeah. So that kind of undesired or unexpected power flow is called parallel path or loop flows. Okay, so this is now what we originally intended. So let's see. Okay, 7-bus case. We have 3 areas, and here left area has 1 bus, right area has 1 bus, top area has 5 bus, and you see the line flow between 2 areas. How much? So 20, 40 megawatt, and the 40 megawatt, and 40 megawatt. So 40 megawatt, 40 megawatt, and 40 megawatt. So you see loop, and actually that loop was not intended. That's the result of power flow. Okay, so so sometimes that is not desirable, and this kind of loop flow increase the losses in the system. Okay, so in multi-area system, areas with direct interconnections can transact according to rules. For example, in Eastern interconnection, in principle, up to nominal thermal interconnection capacity, the transaction is allowed. In Western interconnection, there are more complicated rules. So based on the rules, power transaction can happen, but there is a transaction based on agreement, but the actual power flows through the entire network according to the physical law, impedance of the transmission lines, and ultimately determine what are acceptable patterns of dispatch. So sometimes the power flow, if that matches our previous transaction, that can be compensated or they can be paid, right? So because of the agreement. But sometimes power flow is from the physical law, so there are uncompensated, economically uncompensated flows, because I didn't agree to buy power from you, but just power comes from you to me. Okay, so I don't need to pay that. Right, so that is economically uncompensated flow through other areas. So that is called parallel path or loop flows. Okay, so in the next slide, you saw the example of loop flows. In the case of Orcutt, Texas, because Texas is huge, this is one area, so there is no this kind of connection flow. So, which means there is no uncompensated flow. Anyway, so in this example, from area view, we have top area, left area, and right area. So 40 megawatt, 40 megawatt, and 40 megawatt, and this kind of a loop can exist, which is not good for power losses. So this loop flow can result in higher losses. And this is another case. actually these two areas have a power transaction 100 megawatt. So this is exactly 100 megawatt. But we have another undesired power flows, even though they are very small. And here, yeah, the power losses increase from the previous case. Anyway. Okay, so this is the last topic of before your presentation. We have 40 minutes. I have 30 pages. Great. So optimal power flow. Actually, the level of these contents is somehow not that difficult because you already know familiar with what it is, and you start to read papers, right? So we can go quickly. And today, you need to submit another homework, right? And you have one more homework. Okay. Electricity market. We talked this a lot last semester. So over last 10 years, electricity markets have moved from bilateral contracts between two bodies. Bilateral contracts between utilities to also include spot markets, the real-time market. And spot markets have day-ahead market and real-time market. And this OPF can be used as basis for real-time pricing in major US electricity markets such as MISO, PJM, California, CAISO, and ERCOT. Wow, pretty outdated information. And the electricity megawatt hour is now being treated as a commodity like corn, coffee, cocoa, not cocoa, cocoa, yeah, with the size of the market transmission system dependent. So tools of commodity trading have been widely adopted. So in electricity market, we have option, forward, and hedging. Hedging means there is uncertainty, so you need to be prepared for 2 or 3 different cases. And swap, so this kind of techniques can be used in electricity market as well. And this is an example of electricity futures. So if you have some experience about option, future and option in stock trading, this will be, you may be familiar with this stuff as well. Anyway, and the ideal power market. Ideal power market is analogous to a lake. That means this lake is an energy lake. Okay? The water is energy actually. So generators supply energy into the lake, and the demand just pull out the water from the lake. Okay? They are all connected into one single lake. In that ideal case, we do not have transmission limits. So that is same to economic dispatch. To satisfy demand, how much we need to generate. So yeah, this economic dispatch we discussed last time. Yeah, the simplest one. So 2-bus economic dispatch example, yeah. So 2 generators and 2 loads, and the line is not congested yet, so this is an economic dispatch problem. And in this case, we have a single system marginal price. Okay, so the lambda is 13.02. Yes, so market marginal cost or incremental cost is that, in this example, we have 2 generators. So this is the marginal cost of generator 1, this is marginal cost of generator 2, and we do not have the transmission limit is not binding. So for this price, they can determine the output of the generation, and some of these 2 give you this kind of area supply curve. Real power markets, but different operating reasons impose constraints and may limit ability to achieve economic dispatch globally. And transmission system imposes constraints on the market as well. And so different buses have a different price, right? So that is called locational marginal price. And so marginal cost. Okay, I need to articulate here. So because of the transmission limit, not all generators can operate at the same marginal cost. Because even if this generator is very cheap, if the line connected to this bus is already 100% loaded, it cannot generate further more, right? So we cannot use this cheapest generator in that case, and we need to use another more expensive generator. So because of that, the marginal cost can be different at different buses. And so to consider the transmission limits, this optimal dispatch, optimal power flow should be solved. So charging for energy based on marginal cost at different buses is called locational marginal pricing, LMP, or nodal pricing. If there is no transmission limit constraints, then we have a single LMP, single location, that is called system marginal price, SMP. So in the United States, LMP is common. In Korea, we didn't introduce LMP yet, but maybe sooner or later, I guess this LMP will be introduced. Because what? Why? What is my question? Yes. So why? Why am I expecting? Yes, the transmission constraint is binding. Okay, unless we increase the transmission capacity, that problem gets worse and worse. Okay, so, and then also, the local generation from renewable. So local congestion happens further. So, by the way, this LMP, so when you compute LMP, actually when you solve optimal power flow and know all the dual variables of the generators and transmission line, you can compute LMP from the dual variables. But please do not confuse that dual variables are not exactly same to LMP. Okay? Because LMP includes the generation cost and the transmission. Okay, so LMP comes from the generation cost, and generator has its limit, and also it need to consider transmission limit, okay, another constraint, and also power losses. Okay, so you may think, hey, for this generator, it has lower or upper generation limits, and there is a dual variable for the constraints. So maybe that is same to LMP? No. Okay, we also need to consider the transmission line limits and power losses to exactly compute LMP. Okay? But in some case, when you consider just DC OPF, in that case, LMP is same to the dual variable. Okay? And currently in the US, because they don't know how to solve larger scale AC OPF problem, they solve DC OPF for larger system, and from that solution they use LMP now. Okay. So anyway, pricing electricity, LMP indicates the additional, that's the definition. LMP indicates the additional cost to supply an additional amount of electricity to bus. So that definition, please remember that definition. So, okay, we have a bus, we have a generator, we have a load. And so far we talked about the marginal cost. Okay, for example, this generator, this is the megawatt output, and this is the dollar. So with this kind of minimum and maximum, this kind of supply curve or marginal cost curve, and there is a price, and then you can determine the output of the generator. By the way, oh, turned on. So, yeah, so for to supply one more megawatt, in this case, so we are operating here, and if you increase the output power, then the additional cost to supply 1 megawatt is this one, lambda, right? So that's the meaning of marginal cost of the generator. But when we have, this is connected to another line, supplying 1 more megawatt at this bus may not necessarily imply increasing this generator by 1 megawatt. Yeah, this is not quite a good example, sorry. So suppose that generator is connected to some other buses. So to provide 1 more megawatt at this bus, other generators, okay, so yeah, we can have generator here, but maybe this generator is at its maximum limit. And in that case, if we want to supply 1 more megawatt, other generators need to generate, right? And then you need to consider the marginal cost of the contributing generators, and also need to consider the transmission limits and power losses. Okay, so computing LMP is not trivial. Okay, but now know the meaning of LMP. To supply 1 more megawatt at this bus, what is the cost of the system? How much the cost of the system increases? Okay, that's the definition of LMP. Yeah, LMP indicates the additional cost of entire system to supply an additional amount of electricity to that bus. We will see an interesting example at the end of, almost at the end of these slides. So some electric markets price wholesale energy at LMP. The example is Olcott. Again, this in December 2010. And I think that is if there were no transmission limitations, then the LMP would be same at all buses, SMP then. So that is same to the lambda iteration economic dispatch, the easy problem. And transmission constraints result in different LMPs at buses. So determination of LMPs require the solution of OPF. Okay. So OPF functionally combines power flow with economic dispatch. And minimization cost function, such as operating costs, taking into account realistic equality and inequality constraints. So equality constraints are the active and reactive power balance at each bus, and the generator voltage set point, and the generator limits. And sometimes we have different areas, so you have transaction agreement, so area megawatt interchange constraint as well. So yes, so actually, so far we didn't consider the kind of thing before, but when there is a line and we have some constraints, the power flow, the exact amount of flow on this line, that can be equality constraint. Right? So far when we talk about OPF, we only consider the inequality constraint of the transmission line. But if there is a transaction agreement, then for example, there should be 100 megawatt. So there can be a constraint, area megawatt interchange constraint. About inequality constraints, the transmission line, transformer, and interface flow limits, and generator maximum megawatt limits, maximum and minimum. The reactive power capability curves, and bus voltage magnitude constraints. So in Power World, it solves a simple OPF problem, but using approximated solution. And Power World in 2010, 2010, this voltage magnitude is not implemented in simulator OPF. So anyway, so the control variables are generator megawatt outputs, and also sometimes transformer tap changes and phase angles. So, but when you apply per unit analysis, the transformers are gone, all normalized, and so we didn't care about that. But sometimes this transformer tap change can be variable as well. 초점을 잃어가고 있는 듯한 느낌. So this is an OPF solution method. And I think this OPF solution method is kind of outdated because after that, so this is 2010, and Stephen Lowe developed many techniques. From convex optimization point of view, sometimes convex relaxation is applied. Sometimes the zero duality gap can be achieved, etc. So this is the basic one. Okay. So nonlinear approach using Newton's method can handle marginal losses, but relatively slow and has problems determining binding constraints. So the approximation is linearize the nonlinear curve, and that is used in Power World simulator in 2010. I don't know whether that is improved or not, so please check it on your own. So linear programming, OPF solution method, the solution iterates between solving a full AC power flow solution, but that is not easy, so solving an LP, the approximate version of that. And this is an example of tube bus with unconstrained line. So tube bus, we have line limit, but it is not overloaded, so that constraint is not binding, so that constraint is not active. So with no overloaded, the OPF matches the economic dispatch, right? And marginal cost of supplying power to each bus, so locational marginal price or cost are same because there is no congestion. Then what if the congestion happens? So here with the line loaded to its limit, additional load at bus A here must be supplied locally because so this is cheaper generator than bus A. So, but it cannot increase its output further. So this kind of congestion makes the LMP bus A and B different. Okay. So yes. And 3-bus example. Consider a 3-bus case, and bus 1 is slack. 3 bus looks like it. Slack bus, bus 2, and bus 3. Okay. And the generators and their marginal cost. So for simplicity, we assume constant marginal cost at each generator. So $10, $12, $20. Cheapest one, second cheapest, the expensive one. And assume a single 180 megawatt load at bus 2. Bus 2. Bus 3. This is typo. Yeah, at bus 3. So when we do not consider this line limit, and this is the result, actually so this should be same to economic dispatch. Line from bus 1 to bus 3 is overloaded, this one. And all buses have the same marginal cost, so same SMP. But this is not allowed. This should be avoided. So when you solve it again, by the way, the total cost is this much, 1,800. But no, this congestion is resolved from 120% to 100%. And in previous case, because this is the cheapest generator and it can supply all the demand, 180 megawatt, no, maximum capacity was 400 megawatts, so it generates all the demand. But that is reduced to 120 and 60 megawatt is generated from here, so no, one power flow, another power flow. By the way, even in that case, there is some power flow along that line. Okay, no, not all the generation follow this line because of physical law. So in last semester, you solved this kind of problem before, right? Using superposition. You remember that? Yeah, last semester, power system economics. There were several homework problems like this. Right? Using superposition, you can determine additional power injection follows which direction, considering the impedance of lines. Anyway, so yeah, now the line limits are enforced, and it increases the total cost. And LPOPF redispatches to remove violation. So this is the result. And bus marginal costs are now different. Here, the marginal cost is $10. Here, LMP is 12. And the reason is because the marginal cost of this generator is 12. Actually, there is no load, but you can compute LMP anyway. Okay? And here, the marginal cost is $14. How can you compute it? That's the result. How can you compute the LMP at bus 3? Well, you need to think about how to supply 1 more megawatt at bus 3 at the cheapest way. And the method is to, after you solve the OPF problem, increase 2 megawatt in bus 2 and decrease 1 megawatt at bus 1. And then you still can satisfy this constraint, and then 1 megawatt is supplied to this bus 3. So increase 2, decrease 1, and then so the result. Okay. Yeah, so increase by 2, $24. Decrease by 1, and $10. So 24 minus 10 gives you 14. Okay, so that's why this LMP here is $14. Yeah, so this is the result. Okay, and the power flow slightly changes. Still, we satisfy the transmission line limits. This is more loaded. And still, this generator, the output is 0 megawatt because this is the most expensive one. So we have another way to satisfy the demand. Ooh. So why is bus 3 LMP is 14 megawatt, $14 per megawatt hour? I already explained it to you. Okay. So detailed explanation. And then next is that, okay, the load at bus 3 increases further, 204 megawatt. And to supply that, this line is congested, this line is congested. And I guess, and in this case, what is the LMP of bus 3? No. The output, what is the output of bus 1 and what is the output of bus 2? 100 megawatt and 100 megawatt. But they cannot increase their output further because these two lines are already congested. So we need to use the most expensive one here, right? So the LMP In this case, at bus 3 is now $20 per megawatt hour. Okay. So typical electricity markets. Electricity markets trade various commodities with megawatt hour being the most important one. And a typical market has two settlement periods, day ahead and real time. So day ahead, we solve OPF, we try to solve OPF, and generators, day ahead generators and possibly loads submit offers for the next day. OPF is used to determine who gets dispatched based upon the forecasted conditions, and the result are financially binding, either generator or pay for someone else. But in real time, they have a chance to modify their bid. Okay, so this is day-ahead market, and this is a real-time market. And before gate closure, you have a chance to modify your bid. So actually in Korea, in December, Jeju has this real-time market for renewable generation. Oh. Oh. So payment. Generators are not paid their offer, rather they are paid the LMP at their buses. Okay, well, what do you mean by offer? No, each generator needs to bid. I can generate this amount at this cost, at this price. So each generator generates their bid, and then the market operator collect that and make the supply curve, right? And then supply curve is made, and based on the load forecasting, the amount of required power is determined, and then the price is also determined. So all the generators who bid less than that LMP or SMP, they can enter into the market. So they are not paid as they bid, but they are paid at SMP or LMP. Okay? So you see what I'm saying? So this is not pay as bid. Pay as bid means you bid something and then you get paid by that, but this is not that. So in most systems, loads are charged based on zonal weighted average of LMP. So another complicated rules. And again, each country, each market has their own modified rule. So even if you solve like a OPF problem and you know how to compute exactly LMP, but anyway that will be modified using some customized rules. And at the residential or small commercial level, the LMP costs are not usually passed on directly to the end consumers. Rather, these consumers typically pay a fixed rate that reflects time average of LMP. So as a residential customers, you are not exposed to the fluctuation of LMP, right? You just know for 1 month, based on the total amount of energy you pay, right? And also for industrial customers, we have TOU, right? So that TOU directly reflect LMP, but roughly, long-term sense, it reflects LMP. So whether the price to end customers can reflect LMP or not, or should we do that or not, that is slightly controversial issue. Because if the end customers are exposed to LMP fluctuations, they may not be happy because sometimes the spot price can be very high. Okay? So there is some pricing design issue. And again, LMPs differ across the system due to transmission system congestion. And this is an example of LMP in Midwest. So This is $1 per megawatt hour, which is roughly same to 1 per kilowatt hour. Okay, so you remember that in Korea, S&P is roughly 101 per kilowatt hour. Then in United States, roughly $100 per megawatt hour. So 100 is here, sometimes cheaper, sometimes more expensive. But interestingly, sometimes this LMP can be negative. Why is that? And that kind of negative price really exists even even in Korea. Why? Why? Yeah, plus DR. Yeah, so because there are too much generation, it causes congestion. So we need to reduce the generation or increase the consumption. So if we want to generate more, you need to pay some penalty. Okay, so that's the meaning of negative price. Or if you consume some more power, like EV charging, then you can charge at a cheaper price, get paid. Okay, so this is not a dream, and it really happens in our real situation. Anyway, this yellow, different location have different LMP. Normal case, and further decreases. So another LMP, cheaper price. By the way, what is it? 뭐예요? Yes, that is 오대호, Great Lakes. There are 5 Great Lakes: Michigan, Wisconsin, New York, Pennsylvania, Ohio, Indiana, Illinois, Iowa, Minnesota, North Dakota, Manitoba, Missouri, Kentucky, Tennessee, North Carolina, West Virginia, Maryland, okay, Kansas, Colorado, Nebraska, South Dakota, North Dakota. Where is Texas? Yeah, Texas is somewhere here. Okay. And if you know the color of Michigan, this blue and this red. You don't know what I'm saying. The symbol of Michigan, you are wearing Michigan t-shirts, so blue and yellow. Blue and yellow. Michigan, yeah. Okay. MISO LMP, contour. So cheaper than other areas. By the way, from Smart Grid Com at Glasgow, one professor came from University of Waterloo, and he introduced the power systems of Ontario, and their generation is hugely based on hydro. Yeah, 90% or something like that, so very clean. And also the Ontario, Ontario and the Manitoba, they have this kind of power transaction because two different balancing authority area. Anyway, I guess this should be the last page. So now we have some limitation of using traditional fossil fuel-based generators because of carbon dioxide emission limitation. Okay, so there are 2 different approaches. The first one is carbon tax. Okay, so if you generate power using thermal unit, you need to pay some tax because you emit carbon dioxide. Another one is called emission trading or cap and trade system. That means government determines the total allowed amount of carbon dioxide emission. and then you can purchase this carbon emission right to produce electricity, and you are only allowed to generate up to that point. And if you want to generate more, you can buy carbon emission rights from others. Okay? So by doing that, anyway, from government perspective, they can regulate total amount of carbon emission. And so it has regulation, but also it reflects the market mechanism. Okay? So if you think you can generate more economically than others, then you can buy this emission trading, right? And generate further. Okay. And this kind of regulation should become more severe, I guess. And also you heard the carbon border tax, something like that. So when two countries import some products, then also, and the production of that product already has some carbon emissions, they need to pay tax, right? So this is our field. So we are actually very used to this, but now the ordinary people are also familiar with this kind of concept. Okay. Okay. So I'm pretty happy that we finish the whole basic things before you present your research. And then because by the way, anyway, next Monday we'll have a makeup class here, if the classroom is available. Yeah, and want to share some ideas I got from Glasgow. Any questions? No questions? Then I will see you next Monday. Thank you.